Right. Section 5.2, we've kind of not done section by section here, but section 5.2 really deals with some of the properties of definite integrals and some of their useful concepts. Now, this is definitely just kind of like something that we need to know. We don't truly use these very often. So now that we have a general idea of how to do integrals and what they do, sometimes now it's easier to go back and look at some of the finer details. All right, now that we know what these do. All right, so if we're doing the integral, finding the area of a function, and our bounds are the same thing, so like start at 3 and go to 3, well, our area is going to be 0. You're not finding an area between two things. You're just finding the area of a vertical line, so that would be 0. Okay, if the bounds are the same, the area is 0. Another thing that we can sometimes do is switch our bounds. Okay, we can go from a bigger number on top to a smaller number at the bottom. We can switch it. All we have to do is just put a negative in front. Okay, if you want to switch your bounds, you negate your area. Okay, so usually we let's start on the left and go to the right. If you want to start on the right and go to the left, well, that just makes your area negative. Okay, if you're adding two things inside of an integral, you can split it up into two smaller integrals being added. All right, you keep the bounds exactly the same, but your functions can be split. Now, we don't use this too often. We just kind of like, integrate the big old function all at one time. But if for some reason you needed to, you can split it up into two small pieces. Totally fine. A constant multiplied, we use this a lot in the future. If you just have some constant in front of your function, you can move it to the front, all right, and then just multiply your final answer. So like a lot of times in future lessons, we're going to have like a pi in front of here. It'll be pi times something. And it just gets really messy to have pi in there all the time. So what you can do is just kind of bring it to the front, almost forget about it until the very end of the problem, and then just multiply your answer by pi. So that becomes very, very useful. All right, and then also a good thing that we have is if you have a function from a to b, all right, and you're doing this integral, what you can do is split it up into two smaller pieces at a different value. Okay, you can go from a to c, do that integral, and then go from c to b and do that integral. All right, so being able to split it up into little chunks sometimes is going to be really, really nice and useful. It'll be good for us, I promise. All right, and we can use that idea right here. This is a good idea, and just kind of actually using all these things right here. Let's say we know the integral of an f function from 0 to 4 is 5. We know an integral of f from 0 to 2 is negative 3. All right, so from 0 to 4 is 5, from 0 to 2 is negative 3. A g function from 0 to 4 is negative 1. A g function from 0 to 2 is 2. All right, so to use some of these properties, if I'm doing the integral from 0 to 4 of 3 of my f plus 2 of my g, well, I can split this up. The 3 can move in front, and I can do the integral from 0 to 4 of f plus 2 in front, the integral from 0 to 4 of g. All right, so we can use those little properties to just rearrange the problem. All right, so from 0 to 4 of f, I know that answer is 5. So I have 3 times 5 plus 2 times the integral from 0 to 4 of g was negative 1. So 15 minus 2 is 13. All right, so we can kind of use those properties. Now this one's a little interesting, the integral from 2 to 4. We don't know the integral from 2 to 4 of f, and we don't know the integral of 2 to 4 of g. We know from 0 to 4 and from 0 to 2. So the general idea is if we want 2 to 4, all right, remember how we can break it up into little pieces? All right, so we know from 0 to 4, and we know from 0 to 2, so if we know 0 to 4 and we know 0 to 2, if we subtract those two pieces from each other, that will give us the 2 to 4 part. Okay, so we know 0 to 4 was 5, minus the 0 to 2 part was negative 3. So 5 minus negative 3 is 8. So I need to do 8 minus The g function, same idea. From 0 to 4 was -1. Minus from 0 to 2 is 2. So that's -3. And since it's minus in the middle, I'm going to minus in the middle here. So 8 minus -3 is 11. So we can use kind of some of these properties to break apart integrals, all right, to look at different pieces of them, and to kind of help us solve little tiny problems like that. All right, and some other just general good, useful ideas. All right, if a function, for instance, if the function itself is always bigger than 0, okay, so this function, this red line, is not always bigger than 0, is it? All right, down here is below 0, up here it's above 0. But if I integrate starting at 4 and going to 9, all of that piece is in fact above the x-axis, isn't it? Okay, so the general idea is that if I integrate this function whose values are all above the x-axis, then I would expect that this area is positive. I know that for sure. All right, I will get an answer to this area, and it will be above 0. That goes also the other way. If I do this area from here to here, all of that function is below the x-axis. So this area compared to this area, I know that will be positive, and I know that will be negative. All right. The overall thing I'm not so sure about. If I do the entire thing, the net area, I'm not sure what it will be, whether the negative and positive will cancel out, but I know this part's negative, that part's positive. Okay. All right. If you have two functions, okay, and one of the functions is higher, bigger y values than the other function, well, I know that the area under this one then will be larger than the area under that one. Okay. On that interval, I don't know past that, but as long as one function is bigger than the other, I know the area will be bigger than the other area. Okay. All right. This is kind of a fun idea. Number 3. If you have a function, we can kind of give it a guess for what the area would be. Okay, so I want the area under this thing, and I'm going from -2 to +2. Well, what I can do is I can get kind of an upper estimate, and I can get kind of a lower estimate. Okay, and that's what this stuff says. My area will be bigger than this and smaller than this. Okay, so like the biggest possible area I could have, right, would be this big box right here. Okay, the highest the function reaches times the width of this area, or of this bound. Okay, so the highest this reaches is what, 15, and the width here is 4. So I know my area has to be smaller than 60. 15 times 4 goes up to 15, and it's 4 wide. All right, now that has all this extra stuff in here, so I know the area is smaller. But I also kind of have a lower estimate. The lowest, kind of the smallest spots that I could make that's inside of here, starting here and stopping here, is actually just this little tiny thing. Okay, I can't go higher because I would go above my function. But if I just go, 2 up and 4 over, I know that my lowest possible answer to this would be 8. It's 2 tall, 4 wide, so 8. So this just kind of helps give general approximations. If you remember, kind of like the little Riemann sums we were doing, the little tiny rectangles, all right, we can kind of get an over approximation and an under approximation, and I know my answer somewhere in the middle. This is kind of that same idea. All right, last but not least here, we can find the average height of a function. So the average value of a function. The way we do that is we do 1 over b minus a times the integral, the area of our function. All right, so let's find the average y value on this function x squared on the range 0 to 2. So the average, f average, 1 over b minus a, 2 minus 0, times the integral from 0 to 2 of x squared dx. So 1 over 2 times, all right, x squared, we can do this, would be x cubed over 3 in our bounds from 0 to 2. We plug in 2. 2 cubed, that's 8 over 3. And well, I guess really 8 over 6. So what? 4/3. Plug in 0, that would be 0. So we get 4/3, about 1.3 repeating. So that is called the average height. 1.3 is about here. That is the average height of our function. Okay. Yeah, it gets way up here to 4 and goes way down here to 0. So it's not at 2, the actual average between the highest and the lowest. The idea is it was lower for quite some time, wasn't it? It was below 2, below 1.3 for quite a while, over half the distance, well past 1, right? We're at that low height. But we do this sharp increase right here at the end, all right? So as this sharp increase, it gets really tall, but for a smaller amount of time, okay? So the idea is we can find the average y value by doing this integral times 1 over our parts, all right? We can then use this if we want to find the x value that works. If we say 4/3 equals our equation, we can then solve. So what? Take the square root of both sides. So the square root of 4/3, so 2 over the square root of 3 times by the square root of 3 on the top and the bottom. So 2 square root of 3 over 3. Okay, not a pretty number. So about 1.15. Yeah, that makes sense. 1.5, 1.15. Okay, so we can find average heights using that little formula. And I'll pause it.